Welcome to Mythosium, the channel where we take the most complex ideas in the universe and explain them in a way that feels clear, intuitive, and deeply fascinating. Today, we're diving into one of the most extreme phenomena in astrophysics, spinning black holes. These are objects so dense, so powerful, and so distorted by gravity that even light cannot escape their pull. But when they spin, they become far stranger than anything most people imagine. Black holes are not just cosmic vacuum cleaners. They're engines that can twist space, drag time, power jets across galaxies, and reshape everything that comes near them. Their rotation is not a minor detail. It determines how they grow, how they feed, how they interact with their surroundings, and even how galaxies evolve over billions of years. And recently, astronomers observed something extraordinary, a signal from a distant galaxy that pulsed with a rhythm so regular it seemed almost artificial, repeating every 31 seconds over and over again. It came from a black hole, tearing a star apart, and hidden inside that pattern was a clue about how fast the black hole spins. To truly appreciate what this means, we need to understand how gravity works at the edge of the possible. In everyday life, gravity keeps your feet on the ground, pulls rain down from the clouds, and shapes the motion of planets around the sunday. But near a black hole, gravity becomes something else entirely, so extreme that it bends space like a whirlpool and slows time dramatically. According to Einstein's general theory of relativity, massive objects tell spacetime how to curve, and spacetime tells objects how to move. A black hole is mass concentrated into such a tiny region that the curvature becomes nearly infinite. Now add rotation. When a black hole spins, it drags spacetime with it, a phenomenon known as frame dragging. Imagine swirling a spoon in honey. The honey near the spoon rotates with it. In the case of a black hole, it's spacetime itself being pulled around. Near the event horizon, this becomes unavoidable. Anything that approaches is forced to rotate with the black hole, even if it had no rotation originally. This rotation changes everything. It alters the size of the event horizon. It determines how close matter can orbit without being swallowed. It shifts the boundary where stable orbits are possible. And most importantly, it allows matter to orbit incredibly close, where gravitational energy release is at its maximum. This deeper orbit region is known as the innermost stable circular orbit. The ISCO, is the last safe circular orbit before matter plunges inward. In a non-spinning black hole, the ISCO is relatively far from the center. In a rapidly spinning black hole, the ISCO moves inward dramatically, giving orbiting material the opportunity to circle much faster and much closer before falling in. This difference is crucial, because the orbital speed at the ISCO depends directly on the black hole's spin. If something around the black hole produces a repeating pattern, an oscillation, a hotspot, a bright flash, its timing becomes a way to measure the black hole's rotation. So how do astronomers measure that timing? One of the rarest and most dramatic events in astrophysics is a tidal disruption event. This happens when a star passes too close to a supermassive black hole. The side of the star near the black hole feels a stronger gravitational pull than the far side, so much stronger that the star gets stretched, torn, and eventually ripped apart. Stellar material forms a long stream around the black hole, and as it spirals inward, it heats up to millions of degrees. This produces powerful bursts of X-rays. For a short time, the black hole becomes one of the brightest objects in the universe. Most tidal disruption events produce chaotic, rapidly changing emission. But one event produced something different. A clean repeating X-ray pulse every 131 seconds. It came from a galaxy several hundred million light-years away. The signal persisted for hours, then slowly faded, but its periodicity was unmistakable. And that regular pulse indicated that somewhere in the swirling debris, a bright hotspot was orbiting the black hole. If this hotspot was orbiting close to the ISCO, then the period of its orbit corresponds to the orbital velocity created by the black hole's spin. Faster spins allow shorter orbital periods because matter can orbit closer and harder without being pulled in. Slower spins mean the shortest possible period is longer. By comparing the observed period with the predictions of general relativity for different spins, astronomers could infer how fast this black hole rotates. The result was remarkable. The timing fit a rapidly spinning black hole, one rotating close to the theoretical maximum allowed by Einstein's equations. But where exactly did the hotspot come from? That part of the puzzle is still debated. The most intriguing idea involves a white dwarf, a stellar remnant made of compressed carbon and oxygen. White dwarfs are small, dense, and can survive tidal forces that would rip normal stars apart more easily. If a white dwarf was torn apart in a grazing event, pockets of material might compress and heat into hotspots that orbit briefly before being consumed. Another possibility is that the hotspot came from material in the accretion disk being shock-heated by collisions or magnetic instabilities. As matter spirals inward, it can form clumps or regions of enhanced density. These regions might glow more brightly, orbiting like embers carried in a tornado. Because they're near the ISO, their orbital period matches the observed signal. Regardless of the exact source, the key insight remains. The regular pulsation allowed astronomers to measure the spin of a black hole using a fundamentally new method. And this matters because a black hole's spin is its autobiography. It tells the story of how it formed, how it grew, and what it has consumed. A black hole can grow in two major ways. One is steady feeding, drawing in gas from a disk over long timescales. This method spins the black hole up because the infalling gas orbits in one direction, adding angular momentum. A black hole fueled this way can become a near-maximal spinner, rotating at incredible speeds. The other method is mergers, collisions with other black holes during galactic interactions. Mergers can produce highly chaotic spin outcomes. If the black holes merge with opposite or misaligned spins, the resulting black hole may spin slowly or have a tilted spin axis. If the merger is more aligned, the spin can be stronger. So measuring spin gives astronomers clues about a black hole's history, whether it was fed gently and steadily or assembled violently through collisions. Spin also determines how black holes influence galaxies. Highly spinning black holes can launch tremendous relativist jets. Streams of charged particles accelerated to near light speed. These jets can heat interstellar gas, regulate star formation, and even alter the evolution of galaxies. Slower spinning black holes produce weaker jets, or none at all. Understanding spin is also essential for gravitational wave astronomy. When black holes merge, the waves they produce carry signatures of their spins. Knowing how spins behave in galaxies helps scientists understand the signals detected by observatories like LIGO and Virgo. So when astronomers discovered that a black hole hundreds of millions of light years away pulsed with a clean 131-second heartbeat, it wasn't merely a curiosity. It was a rare glimpse into a phenomenon that usually hides behind turbulence, noise, and chaos. It was a lighthouse-like signal emerging from a storm of destruction at the edge of a gravitational abyss. The physics behind this is profound. Near the event horizon of a spinning black hole, space twists so strongly that the orbital velocities can approach the speed of light. As matter orbits, it emits radiation and relativistic effects like gravitational redshift, Doppler beaming, and lensing shape the appearance of these signals. The hotspot may appear brighter when moving toward us, dimmer when moving away, and shifted in energy by gravitational stretching of light. These subtle distortions create a repeating pattern that reveals the underlying orbital mechanics. Scientists use three main methods to measure black hole spin. One is fitting the shape of the accretion disk's X-ray spectrum, particularly the iron K-alpha line, as iron atoms in the disk emit X-rays. Relativity distorts their spectrum. The degree of distortion depends on how close the inner disk extends to the black hole, and thus on spin. A second method is modeling the continuum radiation, the blend of temperatures across the accretion disk. Faster spins allow the disk to reach higher temperatures, so the thermal spectrum encodes information about spin. The third, far rarer method is timing. If material near the ISO produces a periodic signature, like the hotspot orbiting every 131 seconds, the timing can be matched to theoretical predictions for spin. This method is extremely valuable because it avoids some of the ambiguities of spectral fitting. The new discovery fits into this third category. And because such clean periodic signals are uncommon, each one becomes a crucial data point in understanding how black holes evolve across cosmic time. It suggests that the black hole involved may have grown steadily from accretion rather than chaotic mergers. Its spin may have been shaped by a long history of consistent feeding from a galactic environment rich in gas. Spin measurements like this also help answer one of the biggest astrophysical questions. How do supermassive black holes, millions or billions of times more massive than the Sun, grow so quickly? In the early universe, just a few 100 million years after the Big Bang, quasars already existed, powered by enormous black holes. For them to grow so fast, they must have accreted and spun up efficiently. Observations of highly spinning black holes support this idea. As scientists gather more signals, whether pulses from tidal disruption events, distortions in iron emission lines, or thermal spectra from accretion disks, they can build a clearer picture of how black holes live their lives. At each time a black hole reveals its rotation, it reveals a chapter of cosmic history. Spinning black holes are not just mathematical curiosities. They're fundamental engines that shape galaxies, power quasars, generate jets stretching across millions of light years, and control the flow of energy in the universe. Measuring their spin helps unlock the story of how structure forms on the largest scales. The 131-second pulse was a reminder that even in the most violent and chaotic environments, there can be order. A star was torn apart, its matter stretched into filaments and heated to extreme temperatures. In that catastrophe, a trace of regularity emerged, a repeating heartbeat around a cosmic monster, and encoded in that heartbeat was the spin of a black hole, rotating at a pace dictated by the laws of relativity and the history of everything it had ever consumed. Here at Mythosium, we explore these extraordinary stories because they reveal how the universe operates at its extremes and how much remains to be discovered. If you enjoy learning about the hidden mechanics of the cosmos, make sure to subscribe. There are countless wonders out there, and together we'll continue exploring the physics that shapes our reality. Thanks for watching, and stay curious.